that by the end of class, I think everybody finally got the orthonormal basis written down, right? But then we didn't have time to do the whole adjoint, transpose conjugate, and all that stuff. So, but it's all in the solutions. Am I okay if I leave it to you? Especially if I tell you that, you know, obviously this is a likely thing I might ask you about. You're still okay with it, right? You just need to practice it on your own. Check it out.
No matter what classroom we go to.
I don't know what happened over there. Okay, if you guys are okay with that, I'm going to turn to some of these other questions that are on the review session sheet, and then we can always come back to it later. A lot of the stuff on this review sheet is the more recent material. Some of the stuff we've covered toward the end here. And I'm not going to go in order. I'm going to go in whatever feels like the right order to me. Okay. So that problem was kind of a long one, so I think I want to do something a little faster to do for our next problem, just to kind of move things along a little bit. Okay, so what do I want to do? Okay, so let's try this one. Another example. This is number 9 on the review packet, but so I'm numbering things kind of weird here. So V is again an inner product space, and beta is a basis. Let's say it's got 3 vectors in it, so of course that means the dimension is 3. Okay, and assume that the inner product of Vi with Vj is equal to I times j whenever I and j are between 1 and 3. So if I and j are between 1 and 3, assume that. And then if the coordinate vector of x relative to beta is 3, 1, 0, and the coordinate vector of y with respect to beta is 6, negative 1, 2, then let's compute the inner product of x with y. Okay, we'll try that. The popular, we've done one like this before in group work in class. The popular wrong answer here is 17.
Yeah.
So people like to just dot the 2 vectors together and get 17. But you have to realize what those vectors mean, right? Those columns of numbers, those are the coordinate vectors for x and y respectively. So they aren't actually what the vectors x and y are. So does anybody know how to handle this one? One of the things you should do for sure is go back and review all the group works again. There's only 8 of them. Go back and review the 8 group works that we did this semester. I'd go back to the quizzes again. There's blank copies of all of these things posted. And then obviously redoing the exams would make good sense. And if you go through all that stuff, you're going to run into a problem that's just like this.
Yeah, I remember.
So it's there. Stephanie?
So would x equal like 3g1 like g2?
Uh-huh.
And y would be 6g1 minus g2
Plus 2v.
oh, yeah, sorry.
Yeah, exactly. So that's writing x and y in terms of the basis vectors. Okay. That's what a coordinate vector means, is that those are the coefficients of the linear combination. Okay, so once I've done that, does that shed any light on how to compute the inner product of x with y? Inner product of x with y, I'm going to take the inner product of 3v1 plus v2 with 6v1 minus v2 plus 2v3. And I have my axioms of an inner product, right, that allow me to sort of bust this thing apart. Now in this one I was nice. I made all of all of the coordinates, all the coefficients here were real numbers. If they're not real, be careful, because remember that if you pull constants out of the second slot of the inner product expression, it picks up a conjugation bar. I believe there's a problem on the sample final about that. Actually, should look at the sample final too. I think I mentioned that already. So I'm going to, for example, I'm going to take the 3 and the 6, I'm going to take this first two things, and basically going to FOIL this out. 3 times 6 is 18. I'm just going to get 18 times the inner product of V1 with itself, right? And then minus 3 times the inner product of V1 with V2, and then plus 6 times the inner product of V1 with V3. Okay? And then I have to continue. I actually get 6 terms here, right? So V2, the inner product of V2 with 6V1, and then minus the inner product of V2 with itself, and then plus 2 times the inner product of V2 with V3. Now, the one that we did of these on the, did I do it right? What?
Why didn't you pull up the 6 on the fourth one?
Oh, I have. Oh, this one? Oh, I have no idea. I should have pulled it up. Mine must have been a million miles away. Okay, yeah, I should pull that 6 out.
Now we can try.
Now, on the one that was on the group work, the vectors that were in the basis were already perpendicular, so you could cross a lot of the terms off. But in this one, you can't do that, because I didn't tell you that. All I told you was, here's the formula, right? So you're just going to use this. Easy, right? So you just use that thing to figure this out. So it's just going to be 18 minus 3 times 2 plus 6 times 3 plus 6 times 2 minus 4 plus 2 times 6.
What just happened?
Did I screw it up? No. I'm just using this. So what's the inner product of V1 with itself? Formula says right here, inner product of V1 with itself is 1. 1 times 1. This is a multiplication. Okay? So you're just multiplying. Actually, I and J is not a good choice. Because I looks like a complex number. I should use like VS and VT or something. But anyway, so is everybody cool with that? Of course, I have to make sure I give you something here that's reasonable. For example, the inner product of VI with itself has to be a positive number. So I can't just make anything up here. It's got to satisfy the axioms. But anyway, so this one works out, and you'll get some answer, which I don't know. 50? At least 2 people got the same answer. It must be right. 50. Okay.
Well, we could have done the same mistake.
All right, so that's not too bad. So far, so good? All right. Let's try another one. This is kind of going backwards on the sheet. Number 8 on the same review packet. If T from B to V is linear, by the way, whenever the transformation goes from V to itself, it's often called a linear operator, but that just means linear transformation. So if that's linear, on an inner product space, V, show, we've actually done this before, but I want to just do it again, make sure everybody can still do it, that the null space of T star composed with T is the same as the null space of T. You really want to make sure that your understanding of the concepts are solid enough that things make sense to you. What I mean by that is where people lose lots of points with me is when you write down stuff that does not make any sense at all. So please be aware that this is a set of vectors and this is a set of vectors. And I'm talking about equality of sets. We're not comparing numbers, we're comparing sets to each other. So you need to understand that. This means null space, right? The null space of a transformation. It's really, what is the null space of a transformation again?
All the vectors that get killed by the transformation.
It's all the vectors that get killed by the transformation. In other words, it's the kernel. You can call it the kernel as well. It's just the kernel of the transformation. We're proving that these two transformations have the same kernel. They kill the same vectors. So if I want to show that, how am I going to do it?
So one's not equal to the other.
Set an element in that transformation and it equals 0.
And then
Equals that
also-
one, and then they both equal 0. Something like that.
So,
There's
sort of.
an element in there.
go ahead, Davey.
So yeah, find an element in the null space as the first thing.
Pick something
Show
here.
that it's also in the null
Show that
space
it's here.
of C, and then reverse.
And then reverse, right? Equality of sets, right? Now, we have some tools in this course that can help alleviate that task. Because showing that one thing is a subset of another and then vice versa is like a double proof. If, for example, though, let's say, for example, you know that the dimensions are the same. Because this is actually a subspace of V, and this is a subspace of V. If I have two things that we know, let's say for some independent reason, which we don't know here, by the way, but if we had a problem, and we knew that the dimensions of the two things that we wanted to show were equal, were the same, then we could just show that one of them was a subset of the other, and then we would be done. Because if one of them was a subset of the other, but they weren't equal, then this one would have to have had a larger dimension than this one, right? So they wouldn't have been the same size. So if you know that the dimensions are the same, you cut your work in half. It's not going to happen here, but it might on some problems.
Same with, same dimension for span and line, same for same dimension with, onto and up.
Right, Lisa's reminding us about some of the earlier material. If I give you a set of vectors, and I ask you, are they linearly independent? Do they span V? Are they both, which would mean it's a basis, or neither, right? You can always cross off two of those four choices right away if you know the dimensions that, if you know how many vectors you have, and if you know the dimension of V. Right? Just make sure everybody understands what I'm saying. If I know that I have an n-dimensional vector space, and I know what n is, and I give you more than n vectors, then they can't be Li. And if I give you less than n vectors, they can't span the space. And if I give you the right number of vectors, then it's either both or neither. Right? So you don't actually, in that case, if I give you the right number of vectors, it's both or neither. You don't have to check them both. You check one of them. You check Li. If they're linearly independent, then yeah, great. Then they also have to span the space. You don't have to. I think they called that Annan's consequences, chapter 1. Very worth reviewing. If I've named it after myself, then surely it's something good to know for the final. Let's see. And then the other context where that kind of game comes up is when you have a transformation from V to W, and I ask you, is it one-to-one onto both or neither? If you know the dimensions of V and W ahead of time, right, you will already have a pretty good idea. If V is smaller than W, then your transformation can't be onto. And if T is larger than W, it can't be one-to-one. And if they are the same size, then your transformation is either both, which means it's an isomorphism, or it's neither. So in that case, you only have to check one of them again. You see how there's a very parallel situation there. So I didn't come prepared with a whole lot of examples of that, but you can go back for sure to chapter 1 and look that stuff up. Make sure that you're solid on it. That's something very important to me. I just want my students to really understand that very well. How the dimension, how knowing the dimension of the objects you are working with makes other questions easier to answer. I want people to be able to do that. So, can't get away with any of that here. We just have to go through showing that these two sets are equal. Okay? which way do you want to go first? Starting on the left and going to the right, or starting on the right and going to the left?
Left or right?
Left to right, okay. So prove. I'm going to let x be an element of n of t star t. And we need to show that x is an element of n of t. So,
Wasn't that easy right away? But
say again?
it's gonna go through T first.
So what does this mean? Can we write an equation for this?
T star T of x equals 0.
Right, t star of t of x is 0. And I really want to show over here, x is in the null space of t. In other words, I want to show that t of x is actually 0.
So right there you assume.
So we're proving it this way. So I would claim it's not obvious. So I would like to show that t of x is already killed. I know that after I run it through t star it will be killed, but how do I know it's killed already? Christine? Can I do t star to
T
both?
star inverse.
Well, okay, t star inverse. Okay, this comes under the head. Okay, be very, very careful. Guys, if you're writing, okay. Sorry, Lisa, I'm going to pick on you for a second.
That's fine. But we did a problem where it said that T star inverse was 15.
If I see that or that anywhere on a problem, I better know that it's invertible first.
Oh, oops.
If I don't know something's invertible and I'm writing the inverse of something down, then I'm in trouble. So make sure it's invertible before you write it down. And this is not assumed to be invertible. This is not actually necessarily invertible, unfortunately. I can't assume that. Joseph?
Just apply T adjoint both sides, or T star to both sides, I mean.
You want to apply t so to both sides of this?
Uh-huh.
T star.
So that'll just give me t star of t of x equals t star of 0. No, don't write this down yet. T star of 0, which is 0. Maybe it'll work. I just don't know why it works.
Because T star of T star would be T double star, which is just T, what is it?
T star of t star is actually not t double star, is it? T double star is t double star of. Pardon?
Can you star both sides
Um.
to make it T of?
See, this is really t star squared, actually. It's imposing
Can you
this.
star both? We're assuming that. Can you like star both sides? Like,
You could view this as a transformation, you know, and the star of the 0 transformation would just be 0.
So then it's T of x.
Okay, I guess this comes in, you either studied this yet already or you didn't. This is from your notes from the last week before. So instead of having everybody stabbed in the dark about it, let me just show you what the right thing is to do. What you really want to do is apply the basic definition of the t adjoint again and move the t star to the other side. So here's how you actually do it. If we assume this, right, then this is the 0 vector. So whenever it's in, let's see, how do I want to do that? I'm going to put it in the second slot actually, because I want to shift it back to the first slot. If I take the 0 vector and I inner product that with anything, what will I get? The number 0, right? So the number 0. And what I do know, and I don't maybe know quite what to put in here yet, but do keep in mind what you're trying to show. Yeah, I'll just put a question mark there for now. The reason I put this t star of t of x in the second slot is that then I can move it back to the first slot. If we lose our magic equation,
It's T of x is.
hopefully everybody's getting this one down. I got this learned very well by now. By some miracle, this thing is like a taking a conjugate transfer. Oh, by the way, please do not do anything like that. I saw this on the homework. I don't even know what it means to transpose a linear transformation. I know how to transpose a matrix, but I can't transpose a transformation. So if you want to do something like that, yeah, you have to first put it into a matrix of some type. Then it makes sense to me. Okay, but you don't want to just conjugate transpose a transformation. Anyway, so the point is, see, the reason I put this in the second slot is because I want to take that t star, which is in the second slot, and move it over using the left side of this equation. So what's going to happen is it's going to become t of, well, whatever, I haven't decided what to put there yet, inner product with t of x. Does anybody have an idea what I might want to use for the question mark? Yeah, just x, right? Just x, because then you get the inner product of t of x with itself is equal to 0. How many vectors do you know have an inner product with themselves equal to 0? Only one. Which one, Davey?
0.
The 0 vector, exactly. So t of x is 0. That's a little tricky. But it's only one line long, and you have seen it now a couple of times. So that's a hint.
So whenever we see T star,
Pardon?
and then whenever we see a star, it's probably going to involve that.
Yeah, it involves moving it back to the other side. Like this equation is really crucial. This equation plus the bit about basically conjugate transposing it to get this one. These are like the most important things to know. This is the definition. This is from a definition, and this is from Theorem 6.10.
Could we have solved that using the matrix way, or would there not have been any?
In theory, you could have. You could have written down a matrix representation
But it would be.
for this and a matrix representation. I'd have to think about that as to whether that would be.
I'm just thinking of like the thing you showed at the beginning where we showed a transformation way,
Yeah.
we showed a matrix way.
Right. I mean, it's that's a good point. It's maybe not always totally obvious which way to go with it. Now this one works better just with a direct proof. Now the containment the other way around.
That's the easy part.
Yeah, this is actually the easy part. If t of x is 0, does everybody agree that t star of t of x is 0? Yeah. So I won't even write that up. Just leave it at that. Okay, let's try another one. I'm gonna do maybe one more thing here, and then I do want to move on to some of the other material. Kind of review that as well. So I'm going to go backwards again in the book, or in the review sheet. Let's look at number 7 on the review. Okay, here's what it says. If t from v to v is self-adjoint, then prove that the inner product of t of x with itself is a real number for all x in V. Question. How do you prove that a number is real? If it's not real, what would it be? Complex. So I know for sure that it's at least a complex number. But how would you take, if I gave you a complex number, and I wanted you to prove to me that it's actually a real number, what would be one way to do that?
To square it or take the absolute value of it and show it's positive.
Well, the absolute value of everything is positive.
Not
Complex number, whether it's real, non-real,
squaring it.
whatever.
In one day.
Okay. Right, the conjugate of the number should equal the number. In other words, what I'm going to do to prove this, that's perfect. What I'm going to do to prove this is I am going to put a bar on there and see if I can remove it. Okay? I actually know one good way to remove it though, automatically. Oh yeah, that's a great one. Removed by eraser. No. How can I, does anybody know, think, How can I just take that bar right off of there? Say again? Switch them. Exactly. We have the axiom that says if I switch the order, the bar goes away. Right? So I can start off by switching them, and that will give me that, right? But of course the problem now is the T is on the wrong place. So we really want the T on the left side. If we could get these switched, then we'd actually be done. So we need to get a little clever. We've taken care of the bar, but now we got the T on the wrong side. Hold on, I got a lot of excited people. Allison, go ahead.
Okay, since T is self-adjoint, you can switch it with the definition of the adjoint, which is.
Okay, let's just do one second thing. What does self-adjoint mean?
It means that T is its own adjoint. T star is T.
Yes, T is T star, so we may as well just put it in. Oh my gosh, just like that. I may as well put it in there. I wish I could take this test for you guys. It's so exciting.
You can.
You can make that happen.
I'll be sitting there like bubbling with excitement. Okay, I've got, now, okay, so that seems like a natural thing to do, but then what can I do next? The definition allows me to take it, and I erased it again probably. Well, it's kind of here. The T star moves back to the left side as a T. So this is just T of X with X, and I'm done. One line. Yeah.
Can the T on the right move to the left as a T star? Is that the same thing?
Okay, so the actual definition, let me just make sure I understand your question. The actual definition of the adjoint is that it satisfies that equation. What you're asking me, I believe, is can I do this? Is that right? So this is the definition. This is the question.
Well, because of the definition, you don't necessarily know it's self-adjoint.
Right, and actually, so you're asking me a general question.
Yeah.
Bora's asking me, forget self-adjoint. Just, could you always do that? That would make a great test question. Oh, by the way, I'm not going to ask you guys, like, is this true or false? I mean, I might ask you something like, is this diagonalizable? You know, something that's kind of that nature. Is this a transition matrix? So something like that. But I'm not going to ask you like these conceptual, tricky, true-false items. I will tell you, yes, it's true, or no, it's false. And the answer right now for Bora is this is true. Yeah.
Isn't it because, if you were to write like T star of X, and you were to apply the definition to be T star of X, which equals T? Isn't that all it is?
Well, we haven't technically proved that T star star equals T.
Or was there some class?
Actually, here's the thing. Okay, if you go to the book, see, I didn't really cover all that stuff. You go to the book and you look at the proof that T star star equals T. You're going to need this to prove it. So you're getting into circular reasoning now. If you say, well, I'm going to use the fact that T star star equals T to prove this, because actually, the typical way that this is done is you assume that, or you know this first, and then use it to prove the other one. So do you think, so I've told you this is true. Does anybody have a clue how you might try to prove it? Oh, you guys should have an idea.
Use that standard.
Don't get too specific. I don't want to say what the inner product is specifically. Remember, I know this one. I know this one. What did you just say? Oh, how can I take the conjugate on this? I switch them. I switch them and I put a bar on top. Now I'm ready to work underneath the bar using what I know is the definition. So underneath the bar, this changes to y t star of x. And then guess what you do next?